Hi everyone. I'll step away from the board here to show you the next material that we're covering, Power Series, and I'll give you 15 or 20 seconds to read it and understand it, and then I'll erase it and we can go on from there. Okay, do you have everything? Okay, I think this is the first joke I've actually made in how many lectures? 120 lectures or so of all the courses. Anyway, obviously, I've written things down ahead of time because I don't want to spend too much time with my back to the camera. And this is a proof to a theorem, which we're going to look at. My philosophy of what theorems should be proved, what results should be proved in a calculus course, is that the ones that should be proved are ones where you learn something in the proof. Okay, you learn either something about the method of proof that might be kind of enlightening to life in general or to mathematics, or you learn something about the nature of the problems that we're going to be solving. And I think this is one that kind of satisfies those. And so the other one that we proved rather recently, we've been actually kind of not giving formal proofs, but giving good justifications for almost everything we've been doing. And the one involving the integral test is a really important one to see. You don't want to just do things without understanding them. You want to be able to picture things in your mind as you do them and understand what's going on. So anyway, without further ado, let's as we've been doing in this chapter, we're going to start everything we do by kind of going backwards just a little bit and reviewing what we've done in the past. Okay, so here are 4 different series that we've done before. This first one we did just a day or so ago, last lesson. We used the ratio test, and once we use the ratio test on that, maybe we used it on the flip of it, I can't remember. But anyway, this one, the bottom is growing faster than the top, and the ratio of these things as n goes to infinity is going to go to 1 over e. And since 1 over e is less than 1 in size, that means that every single term is roughly 1 over e times the size of the previous term. And so just like any geometric series, that thing is going to converge then. It converges absolutely. There's no negative signs that it depends on. This one right here, we did not so long ago comparing it to an integral. And when we compared that to the integral of 1 over x times the ln of x, then that one diverged, albeit it diverges very, very slowly. And so that's the answer to that one. This one here, the square root of n, that doesn't get big near as fast as this thing gets big. So 1 over that doesn't get small as fast as this thing gets small. So the first thought you'd say, well, what chance does this have to converge? But you notice it has the negative 1 to the n on it. And so because of that, it converges because the alternate terms are competing with each other. If you have everyone fighting in the same direction, then you can accomplish some things. If you're fighting amongst each other and you're chopping off your neighbor, then you're not near as effective. So this thing converges. It doesn't go off to infinity. It converges to some finite number. And this one would as well, then obviously, if we had a negative 1 to the n on that one as well. So this one does have the negative 1 to an n, so it converges conditionally. And then finally, this is our geometric series again, which quite a while ago now, we showed that thing converges to 1 over 1 minus x when x is less than 1 in size, and it diverges if x is greater than or equal to 1 in size. So the reason I point these 4 out is that I want to distinguish now this last one from the first 3. First 3, either it converges or it diverges or it converges conditionally, okay? One or the other. This one, it depended on the value of x. So you didn't get an answer of one or the other. It said no, it converges for these values and it diverges for this one. So the fact that this thing depends on what you're putting in there makes it different. And that leads us to a generalization of this thing. If you take powers of x, just like this one has here, and you multiply them by something involving your n, Okay, your a sub n. So here they'd all just be 1, but in general you could have something more complicated than just a 1. And so something involving n there, and you add all those things up as n goes from 0 to infinity. That's called a power series. It's called a power series. And a power series converges for a particular value of x. I called it x naught. It converges if we say it converges if, as you'd expect, if when you stick x naught in there, if the series converges. And it converges on a whole set. We say it converges on a whole set. In this case, we called it S. If it converges, if it converges, I got the wrong math symbol there. For all, that's the math symbol for all x in that set. Okay. So in particular, go down here to our geometric series. This thing converges on the set from -1 to 1. Why do we say that? Because you choose any value between -1 and 1, and this thing is going to converge. And anything that's not in that interval, it does not converge. And so we say that this is the, well, we'll get to that later. But in particular, it converges on this set. Okay? So one way of thinking about a power series is it's a polynomial that don't know when to quit. Okay, it's one that don't know when to quit. It just goes on forever. It doesn't stop when this thing hits 10 or 20 or 50 or 100. It keeps going on. So that's one way to think about it, as kind of a generalized polynomial. And also, you should also realize that this thing, just like this as an example, is a function. Any function is a machine. I don't have much room here. But it's a machine where you stick in a value for x and you get out a value. And that's going to be true here. If I stick in a value of 1/2, this is going from 0 to infinity. If I stick in a 1/2 here, this is going to converge to 2. If you stick in a 1/3, 1 minus 1/3 is what? 2/3. 1 over 2/3 is 3/2. So if you stick in 1/3 here for x, it's going to converge to 3/2. So that's what a function is, right? You stick in a number and you get a number out. So that's true for a power series as well. On the set for which it converges, you stick a number in and you're going to get a number out. Okay, so given that, let's prove a very important theorem involving power series. And basically, it comes from asking this question. And again, I don't have much room here. But we say, okay, here's a power series. Here's the interval, say from 0 to wherever, and we say this set S is all the different values for which this thing converges. So maybe S looks like this. Maybe S is a few negative numbers like this. Maybe it's a couple in here. Maybe it's an interval like this. Maybe it's another interval like this. Maybe it includes this endpoint. Maybe it's those things right there. Maybe that's the set S, and it converges just for those values of let me do it in another color here. Maybe it converges just for those values of throw in one more here as well, maybe something like this, okay? Open from there to there. So it could have a collection of open intervals or closed intervals, whatever, and a few other isolated points, and maybe those are all the values where the power series converges, and for everything else it doesn't converge. We have no reason to think at this point that that might not be the case. But this theorem tells us otherwise. It says if you have yourself a power series that looks like this, it's just here. So here again, let me just give you an example of one. Maybe something like this. Maybe it's 1 over n squared plus n all times x to the n. Just something like that. So this is a function of n, and then you're multiplying it by x to the n. So there's another power series. Okay. So suppose you have yourself a power series. Here are the only 3 options. Okay? You only have 3 options. Either this power series converges only at 0. And notice that it has to converge at 0, because if you stick in a 0 here for x, you're going to get x to the 0 power, which is 1. So you're going to get 1 times a to the 0. So you're going to get a to the 0 times 1. But all these other values of x to the n are going to be 0, so the whole power series converges just to that number. Okay? So at the very least, they're all going to converge at 0, because that's what's going to come out. Okay, so that's one option. The other option is that this series converges for any x that you put in there. For any value of x, this thing is going to converge. Okay, that's the second option. And then the third option is, if it's neither of those two extremes, then here's the nice thing about it. Instead of having a collection of places where it converges, which is maybe a few different intervals and some other isolated points, things like that, it says no, 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 no. If neither of those other ones, here is your only option. Your only option is that the places where it converges is all centered around the origin with some distance, which we call r, where r is the radius. It's called the radius of convergence. We'll get to that. But basically it goes this r in this direction and r in this direction, and it converges for everything in there, and it diverges for everything out there. So it says the world does not look like this. It looks like this instead. And maybe the endpoints are included, maybe not. Either one of those is an opportunity, is a possibility, but everything outside of that, it diverges, and everything inside, it converges. And not only does it converge, but it converges absolutely for everything inside there. Okay? So as I say, let's go ahead and prove that one. And here's the way the proof goes, and it's nothing that you need to know all these details, and you don't have to get all hot and bothered if you don't understand the whole thing but if nothing else, you see here's how a mathematical proof in analysis looks, and you get kind of an appreciation for just the whole process of proving things. So here's what we need to prove. We need to prove that one of these three things is going to occur. So the way we prove it, we say, okay, suppose that 1 or 2 do not occur. Okay, suppose it's not one of those. Then we have to prove that this one will occur. That is, that there is this radius where it converges for everything inside and it diverges for everything outside. Okay, so we're going to assume that that's the one we have to prove is going to happen if 1 and 2 don't happen. So here's what we do. We say, let R be, here's something you haven't seen before. It's called the least upper bound. You know, you hopefully remember what an upper bound is. If you have some set like this, an upper bound is just some number which is bigger than, greater than everything in this set. So if this is my set right here, an upper bound for it, if this thing stops at 3 right there, then 5 would be an upper bound. 4.5 would be an upper bound. 170 would be an upper bound. Anything which is greater than or equal to everything in this set is called an upper bound. Once you have all those upper bounds, the L stands for the word least. It's the smallest. It's the least upper bound. So 5 is an upper bound, 4 is 1, or 4.5, 4, 3.5, and so on. But notice that the least upper bound for this set is going to be 3. Because 3 is an upper bound. Everything is less than or equal to 3. But there's no other upper bound which is smaller than that. If I go anything smaller, it's not an upper bound. So 3 would be the least upper bound. And it doesn't matter whether 3 was included in that set or not, because you just need something which, an upper bound is something which is greater than or equal to everything in the set. So if the set included 3, 3 would still be your least upper bound there. Okay? So with that as a very brief introduction to upper bounds, that's what we're going to use. We're going to let R be the least upper bound of the absolute values. So now you can go in either direction, to the left or right, absolute value of all the values of x for which this thing converges. Okay? So R is the least upper bound of all the values of absolute value of x for which this thing converges. Okay? So we're going to choose something which is less than r. So here's let's say that r is equal to 3. Okay? R is equal to 3, and we're going to choose a value of x which is less than r. So here's a value of x right there, which is less than r. And since it's less than r, we can find there exists, that's the mathematical symbol for there exists some s which is between x and r in size. And these could either be positive or negative. I'll just, for sake of simplicity, I'll just stay all positive here. So basically, since this thing is less than r, whenever you have two real numbers and one number is less than the other one, you can always find one in between. Okay, you can always find one in between. So here, since this thing is less than r, I can find one in between right there, and that's good. This is my x, and this one right there is my s. Okay, they're both less than r. So there's something in between. Okay, and what do we know? We know that this thing is going to converge. Why is that? Because if it didn't converge, then r would have to have been smaller than that. Because everything less than r, this thing converges. So as long as this thing is less than r, by the very definition of r, this thing is going to converge. Okay, so we know that converges. Now we just do a little bit of algebra. Okay, we say, okay, let's take this thing with x to the n in it, and let's both divide and multiply by s to the n. See that? So I'm taking my x to the n, that's right there. I'm dividing it by s to the n, and I'm also multiplying it by s to the n. Okay? Algebraically I can do that, so that's fine. And now, since this thing is converging, we know from what we've done earlier in our lessons that if this thing converges, that the individual terms have to go to 0. We usually apply the contrapositive. If the individual terms don't go to 0, then we know this thing diverges. The contrapositive is, if this thing converges, then the individual terms have to go to 0. We proved that in the very first day of series, I believe. Okay? So we know those go to 0. Since they go to 0, we know they have to head in that direction. What does it mean for a series of things to go to 0? Here's 0 right here. It means, remember what the idea of a limit is? It means that you give me a little interval around it, and eventually everything is going to be inside. Okay, so since the limit is 0, eventually everything's going to be inside. So if you go far enough out, there exists some capital N. If you go out far enough beyond some capital N, then as long as you're beyond that, everything is going to be inside here. Everything is going to be less than 1 in size. Okay, so that's why I like this proof, because it kind of reinforces all these things that we've been learning all along. Okay, so for n greater than n, what do we have? We have that this thing right here is less than or equal to, these things are all less than or equal to 1, so this thing here is going to be less than or equal to this, and this thing right here is equal to this. That's the same. So that means that these things here are all going to be less than or equal to x over s to the n. Okay? Because these things here cancel out. I get an x to the n, all is less than or equal to this. Now, what's the key? The key is, notice how we're using the geometric series. X is less than s in size, so this thing right here is less than 1 in size. Okay? The size of that is less than 1. And what do we know is true? If you have anything that's less than 1 in size, it's going to converge. So this thing here converges, and since all of these things are less than or equal to all of these things, and they're all positive, that means that this thing also has to converge. And notice that it converges absolutely. See that? With the absolute values on. So it converges absolutely. And so there it is. So it converges absolutely. Okay? So what do we have? We have that if you have anything less than r, then it's going to converge absolutely. What if you have anything greater than r in size? Well, what did we say? We said that r was an upper bound for all the places where it it converged. So if it did converge anywhere out here, if that's another spot where it converged, then your R would have had to been out there, because R has to contain all those places where it converges. So just by the definition of R, everything outside of it is a place where it diverges. Okay? So there you go. Kind of cool. Let me make sure you're all with me here. Okay, you all good? You all are? Thank you. You didn't go away. So here's this R. R is called the radius of convergence. Okay? And we want to be able to say that every power series has a radius of convergence. So in this case, we just say that R is equal to 0, which means the only place where it converges is 0. And here we say that R is equal to infinity, which means that anywhere along the whole real line is going to converge. And then if it's not one of those two cases, then R is some finite number. Now, notice that we have not talked about the endpoints, okay? We know everything inside converges absolutely. We know everything outside diverges. But what about the endpoints? And the answer is anything can happen at the endpoints. It might be that it doesn't converge at either endpoint, so that the places where it converges is an open interval. It might be that it converges at the left hand, the negative endpoint, right here, negative R, but it does not converge at R. It could be the flip. Maybe it doesn't converge there, but it does converge there. Or maybe it converges at both of them. Okay? But whichever one it is, that is called the interval of convergence. So the interval of convergence is, just as the name implies, it's the entire interval for which the power series converges. Okay, so the interval might be closed on both ends. Maybe it's open, or maybe it's closed on one end and open on the other. We'll see examples of all these things. Okay, so there you go. Okay, well, that was a lot of writing. I'm glad that it's all available on YouTube for eternity, because it's kind of neat stuff. Okay, very good. Glad I didn't try to write that as I was talking. So now let's look at some examples that illustrate each one of these. Okay, and these are examples that I always give to my class to do when I teach a class, but since I have no control over all of you, I'll have no choice but to do them for you. So there's the power series. Let's find out what the radius of convergence is. So for almost all of these, we're going to use the ratio test, and watch how we do it. How does the ratio test work? We take the n plus first term. See that? Divided by the nth term. And we slap on absolute values, because we're looking, x can go either positive or negative from 0. So this is going to be the limit as n goes to infinity. And see once what happens here. Here's the limit as n goes to infinity. Notice that this cancels with all these, and I'm left with n plus 1 right there. And this is going to cancel with all of these, and you're going to be just left with an x right there. And so I look at that, and I say, what is that limit? And I notice that obviously when x is equal to 0, the limit is 0. But you give me any number other than 0, and you multiply it by n plus 1, and you take the limit as n goes to infinity, that's going to haul off to infinity. And all we have to know is that this is greater than 1, and so this ratio is greater than 1, which means that this thing diverges for any value of x other than 0. So the only place, so the radius of convergence is 0, and the interval of convergence is just the point 0. Okay, so there's that one. Okay, let's flip it around and put this in the denominator instead. Okay, what's that one going to do for us? Well, do the same thing. Take the limit x to the n plus 1 all over n plus 1 factorial, all divided by, so you flip it, x to the n over x to the n, slap on absolute values. What do we know? We know that as long as that ratio is less than 1 in size, the ratio test applies for positive things. So put on the absolute values, and these are the positive, everything is positive here. And you take the limit here as n goes to infinity, and what do we get? You're going to get an x on the top, and you're going to get an n plus 1 on the bottom. Agreed? And now you look at that and you say, no matter what x is, x could be 147. 147 divided by n plus 1, that limit as n goes to infinity, is equal to 0. All we need is for the limit to be less than 1, and we got it in spades. It's equal to 0. And so this thing converges for all values of x. So that we say the radius of convergence is infinity, and the interval of convergence we would write like that. Okay? Let's try another one. All these things I'll assume start at 0 now. So we can use, actually there we could use the root test as well, but let's just go ahead and use the ratio test again. So the ratio test is x to the n plus 1 all over 7 to the n plus 1 divided by the nth term, which is 7 to the n all over x to the n. Slap on absolute values to make it all positive. And what do we end up with? You notice we're going to get an x on top, we're going to get a 7 down below. What do I know about the ratio test? I know that the ratio test tells me that this thing converges as long as this limit is less than 1 in size. So that's true. That's just using what we already know. Everything is positive. We're looking at these things. As long as that's less than 1 in size, this then with the absolute values it's going to converge. And if it converges absolutely, it converges. So we just want this to be less than 1 in size. And so what does that imply? It implies that x is less than 7. So there's your radius of convergence. And now we need to find the interval of convergence. So if you stick in 7, notice you're going to get 7 to the n over 7 to the n, which is 1. So you're going to add up 1 plus 1 plus 1 plus 1 plus 1. It's going to add up to infinity, go off to infinity. If you put in x equals negative 7, you're going to get negative 7 to the n. Look what you're going to get. Negative 7 to the n over 7 to the n, which you can write, combine those together, and you're going to get negative 1 to the n. And negative 1 to the n, remember what happens there? Negative 1 to the n going from 0 to infinity. It's going to be 1 minus 1 plus 1 minus 1 plus 1. So when you add them up, it's going to be 1. And then add those 2 up, 0. Add those 3 up, you get 1. Add those 4, you're going to get 0. So the point is, the partial sums are not going to 0. Partial sums are bouncing between 0 and 1. So it does not converge at either endpoint. And so here we would say the interval of convergence is negative 7 to 7. Okay, neither endpoint. Okay, how about this one? Okay, it's going to be similar to the previous one. Take the limit as n goes to infinity, x to the n plus 1. By this time, by the way, you should be doing this before you watch me do it. Okay? Mathematics is not a spectator sport. Okay? 7 to the n, x to the n, slap on absolute values. So basically what we're doing again is we're saying let's make this all positive things by slapping on absolute values. And once we do that, let me just do this one a little more carefully. I've been talking about it, but let me just say it. Okay? So here let's say we're going to look at this one. We're going to look at that one. See when this thing converges. These are all positive. So since these are all non-negative terms, we can use the ratio test on it. And so what does the ratio test say? It says you take the n plus first term divided by the nth term all these things have absolute values, notice. So there it is. And now what happens? As n goes to infinity, you're going to get an x up on top. That's the only thing that can be negative, so I really only need to keep the absolute value around that. Here you're going to get a 7 on the bottom, and then you're going to get n over n plus 1. And what happens to that as n goes to infinity? This thing goes to 1. So this whole limit just becomes this. And what do we know about this thing? The ratio test tells me that this thing converges whenever this thing is less than 1 in size. So if I multiply through by 7, I see that it's going to converge. This is going to converge whenever x is less than 7 in size. If this thing converges, then this thing converges. We proved that one a while back, that if it converges absolutely, then it converges. So we would finally just say that this thing here converges absolutely. First of all, the radius of convergence is 7, because that's your cutoff points. And now we know it converges absolutely for all x's in here. So let me draw it here for you. Here's -7. Here's 7. We know anything in this open interval is going to converge absolutely for everything in there. What about the endpoints? The endpoints we have to check separately. Okay? Can you just follow me if I do it with my finger? If x is equal to 7, you're going to get 7 to the n over 7 to the n, which is 1. So this is just going to be the series 1 over n. That's your harmonic series. You know that the harmonic series does not converge. Okay? On the other hand, if I have -7 up here, -7 to the n over 7 to the n cancels the way I did it a few minutes ago, and that becomes -1 to the n. So that all just cancels into this. And there's your harmonic series again, but now it's an alternating harmonic series. And so what's true? 1 over n, those things go to 0. So when you alternate the sign, it converges by the alternating series test. So here is your interval of convergence, right there. Okay? So there you go. Okay? The last two I'm going to leave for you. I'll give you the answer, but see once if you can figure it out on your own. Okay? Here's what I'm going to do first of all. I'm going to write it as negative x to the n. I think it's just negative is all I want. Oh, all right. Yeah, I'm sorry. -1 to the n times x to the n all over n times 7 to the n. Okay? I don't know. Let's go ahead and do it. So you slap on absolute values there. And what happens when I take the limit as n goes to infinity of this thing to the n plus first power divided by this thing to the nth power slap on your absolute values as we did before. What happens to all that? Well, let's see. Get rid of all these. You're going to get a 7 down there. These divide out with all these, and I'm left with a -1, but the absolute value of a -1 is just 1, so that disappears or goes away. And then I have your x up here, same as before. And I have what? N over n plus 1. And again, That's going to go to 1 as n goes to infinity. So this limit is the same as we had before. And as long as that thing is less than 1 in size, we've got ourselves a radius of convergence. Now, the only difference is that when we look at the endpoints, the endpoints are going to change. Now, when you stick in -7, the -7 together with this thing is going to give you a 7 to the n. 7 to the n over 7 to the n is 1, so it does not converge on this side. But when you let x be 7, then you're going to get 7 to the n over 7 to the n, which is 1, and now you do have a negative. So you're going to get an alternating series on the right-hand side. So it's now going to look like that. So all that did was switch the endpoint. And now, can you guess the last one I'm going to do? I want one that's going to have an interval of convergence like this. What's going to do it? What's going to do it? Can you see it? It's going to be x to the n over 7 to the n, and now I'm going to put an n squared down there. And by putting an n squared, now it's going to converge at both of the endpoints, and so there's your interval of convergence. Okay? So there's basically all the options, okay? Either interval of convergence of 0, or the whole real line, or open on both ends, closed on both ends, or one of them open, one of them closed. Okay, finally, this is a long video, a long recording, but you're hanging in there, that's good. Okay, you can turn it off and grab a cup of coffee as needed. Let's look at some examples. Let's look at that one. What's the radius and interval of convergence of that? Okay, it's a power series. We know that if you didn't have this there, then the radius of convergence would be 1. So how does this change things? The fact that you're dividing by a big old power of n there, how is that going to affect it? Is that going to grab some more values of x? Let's see once what happens. X to the n plus 1 all over n plus 1 to the 100th. Flip it over, n to the 100th divided by x to the n. Take the absolute value, take the limit as n goes to infinity. Start doing these pretty fast, you're going to get just an x like that. And now I'm going to write that as n over n plus 1 all to the 100th power. Okay? This is a fixed number. So this inside is going to 1, and as this thing goes to 1, 1 to the 100th power goes to 1. As this thing goes to 1, you take it to the 100th power, it's going to go to 1. If you were to multiply that whole thing out, you're going to get n to the 100th up here. And here you're going to get some humongous thing, but the highest power is going to be n to the 100th, and then these other ones are lower powers. So then you can divide both the top and the bottom by n to the 100th, and you can get the result that way as well. Okay, so the point is that all goes to 1. So this limit is just equal to x. What do we have? Look at there. This thing here doesn't affect the radius of convergence one bit. Doesn't affect it one bit. It does affect the interval of convergence. The interval of convergence is going to be from -1 to 1. Because you stick in a 1 there or a -1, it's going to converge. But it doesn't affect the radius one bit. So that goes back to my point that these things are just super powerful compared to any power of n. These things just dominate. They don't even feel it. Except for those endpoints, they don't even feel the presence. Okay? Let's do another one. Okay? Hopefully these are starting to look kind of familiar. Okay, I'm a boring guy. Just have the same ideas that keep going through my mind all the time. It's kind of nice about mathematicians in general, maybe. Okay, we have that divided by the nth term slap on the absolute values. Make sure in your writing that you have limit here equals this limit. Don't just have stuff without limit there. Be precise in your thinking and be precise in your writing, okay? So what happens here? You're going to get 1x all by itself left. Then what else happens? So that takes care of all those things. Then this goes with this, and you're only left with an n plus 1 left. Agreed? Here you're going to get an n plus 1. So you're going to get this thing to the first power, and then you're also going to get this thing to the nth power. So this all goes with this, and I'm left. Okay, my computer gave up on me, but I caught it right away. So see where we are here. So we're going to get an x, and then here you had a n factorial that canceled with these, leaving out a n plus 1 here. You had an extra n plus 1 here, which canceled with that, and you're left with n plus 1 to the n all over n to the n, and so you get that. And now you remember this thing. That's if you divide the top by the bottom, you get 1 plus 1 over n to the n, and recall that goes to e. Okay, so this all goes to e. So that's going to be this thing times e. What does the ratio test tell us? It tells us that this thing converges whenever that's less than 1 in size, which means that x is less than 1 over e. So there your radius convergence is 1 over e. And as soon as you start getting more complicated things here with involving factorials and so on, finding the interval of convergence is very difficult. We won't bother with it. So whether it converges at the endpoints or not, I'm not sure. I had a student years ago who was really interested in that. He spent a lot of time working on some fancy stuff. He's now got his doctoral degree from Berkeley in galaxy formation, modeling that, and is over at in the Netherlands, I believe. He's got a list of 300 publications or so. So anyway, as I recall, he worked on that, but that was 30 years ago and no one since. Okay, so there's that one. Let's do two more. Let's do one that's just a little more ambitious, and just see the kinds of things you can do. N to the 2n times n factorial squared. Oops, I'm sorry. Times x to the n all over 4n factorial. How does that look for something kind of intimidating? Okay, let's find the radius convergence of it. So as I say, I like these things because everything it's just like cleaning fish. You get rid of all the unnecessary, unwanted parts, and you see what's left. So here we go. So you got to be careful. Every place you see an n, you got to put n plus 1. So let me do a couple things in my head. When I put an n plus 1 in there, it's going to end up being a 2n plus 2. Agreed? Then it's going to be an n plus 1 factorial quantity squared. There's no n there, it's just squared. Then x to the n plus 1 all over. Again, if I put an n plus 1 in there and multiply it by 4, it's going to be a 4n plus 4. I could do that in 2 steps, but I'm just going to make it 1 step. It's going to be a 4n plus 4 by the time I do that. And now you flip everything over, it's going to be a 4n factorial all over n to the 2n, n factorial, quantity squared, x to the n. And you see what you can do by way of getting rid of all the unnecessary stuff there. So let's start with the x's. That's going to give us a square root of, an absolute value of x. How about this and this? Each one of these things is going to have an extra n plus 1 to it. Agreed? So I can get rid of both of these, and I'm going to be left with an n plus 1 quantity squared. Agreed? How about these? Notice I have two more of these things than I do here. So I have a couple more, n plus 1 squared. That takes care of those two. And then I'm left with n plus 1 all over n to the 2n. That's what I'm left with. So that takes care of all this and all that. Now, finally here, what happens? This thing here, notice I can write as 4n plus 4 times 4n plus 3 times 4n plus 2 times 4n plus 1 times 4n. And as soon as I get to the 4n, I'm just going to have all those things that are upstairs that are going to cancel with all these things. So all that I'm left with is just going to be these. 4n plus 4, 4n plus 3, 4n plus 2, 4n plus 1. There you go. Now what can we do? Well, I think let's try to do it all at one step here. This is going to be x. Notice that these things here, if I multiply them all out, I'm going to get an n to the 4th power. See that? If I multiply all these out, I'm going to get an n to the 4th power. So this polynomial in n is exactly the same degree as this one, except the only difference is that this one has a 4 times 4 times 4 times 4 in front of the n to the 4th. See that? So I'm going to get an n to the 4th on top. I'm going to get a, what's 16 times 16? 256. 256 n to the 4th on the bottom. And then the other are all lower values of n. So as n goes to infinity, you can divide both the top and the bottom by, or multiply by 1 over n to the 4th. And that gets rid of all these things. And I'm just going to be left with a 1 up here and a 256 down there. So there's my 256, which is 4 to the 4th. Okay? Finally, what about this thing? Notice that I can write that as n plus 1 to the, or let me do 2 steps in one. 1 plus 1 over n all to the n power. And then that's going to be squared. Because if you take this thing and you square it, you multiply the exponents and you're going to get a 2n. This thing here, hopefully you realize, goes to e, so you're going to go to e squared. So that's going to give you an e squared up there. Okay? So what do we know? We know that this thing is going to converge whenever this is less than 1 in size, which means x has to be less than 256, all divided by e squared. So there is your radius of convergence. And again, I wouldn't bother trying to figure out what the interval of convergence is. I wouldn't. You may if you like. Okay, there you go. So there's that one. Okay, I will leave you, before I do one last problem, here is a problem I'll give you, which is just one, about the same thing, but just one step messier than this one. There it is right there. Make sure you have it written down there. N to the 100th, n to the 2n, 2n to the n factorial squared, x to the n, all over 5n factorial. Okay? So it's done pretty much the same as this one, just as I say, just a little messier yet, but see if you can do it. Okay? There you go. Okay? So let's see. Let me leave that one up here just so you've got it. And look, here's the last one I want to do, just to show you what else you can do here. All our power series have all just been powers of x. what if instead of powers of x, you have powers of x minus 3? If you remember from pre-calculus, all that's going to do is just translate everything over so that instead of being centered at 0, it's now going to be centered at 3. So it's the same idea, it's just translated over. So let's go ahead and find the radius of convergence and the interval of convergence of this one. So here's what we do. Take the limit as n goes to infinity. And I tell you what, let's just make it an n on the bottom. Let's make it a square root of n on the bottom, just to make it a little bit different. Okay, square root of n on the bottom. Okay, here we go. So it's the limit of the slap absolute values, x minus 3 to the n plus 1, all over the square root of n plus 1, times 5 to the n plus 1, all divided by square root of n, 5 to the n, and x minus 3 to the n. Okay? You do all the cleaning of the fish, and what are you going to be left with? You're going to get an absolute value of x minus 3 when those go away. These are going to give you a 5 down there, and then you're going to have the square root of n over n plus 1. But this thing goes to 1, and so the square root of that goes to 1, so you just end up with that right there. And so this will converge absolutely whenever this thing is less than 1 in size. So let me just go up here, and so you're going to get x minus 3 is less than 5. I've taught calculus enough to know that you have Calc 2 students who can do all this sophisticated stuff with series and sequences, but when they finally get to this, they are stuck because they don't know their algebra. Here's the way you handle this. You just say if the absolute value of anything is less than 7, that means that that thing has got to be between negative 7 and 7. Agreed? So this thing here, x minus 3, has got to be between 5 and negative 5. So you write that out, and then you just add 3 to everything. If you add 3, you're going to get negative 2 less than x. Add 3, you're going to get 8. So the radius of convergence, we still say the radius of convergence is 5 because you're starting at a different center. You're starting at 3 now, but you're going 5 in this direction to get to 8 and 5 in this direction to go to negative 2. And so the radius of convergence is still 5, okay? And now your interval of convergence, notice it's everything from negative 2 to 8. So here's negative 2 and here's 8. Now we have to check the endpoints. If you stick in 8, 8 minus 3 is 5. 5 to the n over 5 to the n is 1. So you're just going to get the series 1 over square root of n. The p-test tells us that that doesn't go to 0 fast enough, so it is not going to converge at 8. On the other hand, if you stick in negative 2 minus 3 is negative 5. Negative 5 to the n over 5 to the n. Negative 5 to the n over 5 to the n is equal to negative 5 over 5, which is negative 1 to the n. And so you're going to end up with I'm running out of space here. You're going to end up with just negative 1 to the n all over the square root of n. And there your alternating series comes into play because 1 over square root of n monotonically goes to 0. And so this thing is going to converge. So there you have it right there. Okay? So there's everything you need to know about finding intervals of convergence. I shouldn't say that because in the next section we're going to say this. We're going to say, hey, didn't we all agree that this thing is indeed a function? If I wanted to, I could just say, call it f of x. Here's my function f of x. This f of x has this as the domain. For any value you stick into f, you're going to get a number out. So it's a function on this interval of convergence. Well, what do we know from Calc 1 that you can do with any function? You can ask what's the derivative of it, and what's the antiderivative? What's the integral of it? Okay? And so that's what we're going to do. And these are all important things. These are things that engineers and physicists and so on use a lot in solving real-world problems involving the real world, the natural world. So, how is this going to affect things? Is it going to affect the interval of convergence? How do you go about doing it? So a lot of good stuff coming up. We will see you in the next lesson.